let's talk about the different conformations for cyclohexane. So you would remember from when we did cycloalkanes, right? Cyclohexane, this is cyclohexane, your 2D structure, right? Molecular formula C6H12. Okay? Now, cyclohexane has different conformations, right? There's the boat conformation, which is shown over here, and there's a chair conformation, right? Now, let's remind ourselves of what conformations are, right? Or conformational isomers. They have the same molecular formula, right? These two, they're both C6H12, and the connectivity is the same, right? But there's something different about the orientation of the atoms in space. You don't have to worry about in space. It's just that the orientation is different. So these two, the boat and the chair, they're conformations of cyclohexane. Now, if we take a look, this is carbon one here. Oh, I love yellow, but let's do red. One, two, one, two. And you can do this for all the carbons in this structure, right? So if we look at carbon number one here, we have two hydrogens bonded to a CH2 to a CH2. Same thing here. So the connectivity is the same, and it's the same thing for carbon 2 here has that bonded, and these two hydrogens, same thing, two hydrogens, CH2, CH2. The connectivity is the same. Same molecular formula, same connectivity. But if we take a look at this carbon and this carbon, you see that they're oriented differently. Same thing with this one and this one. The orientation is the same, which is what makes them conformers or conformational isomers. Okay. Now that we've established that these are the two conformation of cyclohexane, the boat and the chair. One of them is more stable than the other, right? Your chair conformation is more stable than the boat. So the chair conformation is more stable than the boat. Here's why. Your chair conformation is strain free. There's no strain, right? Torsional, there's no torsional strain. There is neither one of these, neither the boat nor the chair has any angular strain. Their angles are relatively close to 109.5. So there's no torsional strain, no angular strain in either one of these, right? However, and if you have forgotten what torsional strain is and angular, you can go back to my videos on angular strain, torsional, and steric strain, right? So there's no strain in my chair, right? Let's talk about the torsional strain that exists in the boat conformation and explain why it's not in our chair conformation. To do that, let's do this. Let's do this first. Let's number our carbons. This is carbon 1. This is carbon number 2. This is carbon 3. This is 4. That's 5. That's 6, right? Let's number or carbons on this molecule. That's carbon 1, that's 2, 3, 4, 5, 6. Here is why our boat conformation has torsional strain and as a result is not the most stable conformation, right? Here's why. Let us take a look at, let us focus our attention on carbon 1 and carbon number 4 in both the chair and the boat conformation, right? In your boat conformation, you will realize that your hydrogens, they are eclipsed, right? If you have forgotten what eclipse is, go back to the lesson with eclipse and staggered conformation. So the hydrogens are eclipsed. Here's what happens. In this position, right, because they're so close, that's how you get the torsional strain. Because what's happening, let's just look at it simply. These are close, So in order for them to be this close to each other, the molecule has to strain for them to stay this close, the molecule has to strain. That's why we have torsional strain. Plus the hydrogens are eclipsed, right? All the eclipsed molecule has torsional strain, as I would have explained in my prior videos, right? But let's take a look. Let us hop over here now to our shear conformation. Yeah. So if we look at carbon 1 and carbon number 4, the same hydrogens, and I'm going to call them hydrogen A. Let's do red. I think you see this better. Call that A and call this hydrogen B. If we call this A and B over here, look what's happening. This hydrogen and this hydrogen, they're not eclipsed. They're what we call staggered. If you have forgotten what staggered is, go back and watch the video with staggered and eclipse conformation. But it's literally what the word means in English. It means that this hydrogen and this hydrogen right here are staggered to each other. Here they're eclipsed, right? They're literally facing each other here and are so close. They're here. Here they are eclipsed and they're facing each other. So in essence, the little electron cloud that is here is repelling. So the molecule is unstable. Let's just put it that the molecule is in chaos. Electrons they have the same charge. So you put two negative things together, they're going to repel. That's what's happening here. If you have repulsion, it's causing chaos. This molecule is unstable. Over here, those same two hydrogens are staggered. In this position, the little electron clouds can't repel each other, so the molecule stays stable, which is why your chair conformation is the most stable conformation. Now, as you take your organic course, it's important that you're able to see 3D, and also you got to be able to make models. It would really help. I suggest you buy molecules, right? The little ball and stick, that's what I'm talking about. Buy your ball and stick molecules. You're gonna need them. I promise you, it makes things easier to see, so you should buy them. So let's now, since it's important for you to be able to identify chair and a regular, even if it's your 2D, in a ball and stick model, let's look at a boat conformation for your ball and stick and a chair conformation for your ball and stick. And we're going to match it to the 2D so you see the correlation between the two. So let us bring up, let me bring up my boat conformation. All right, so let's do this, right? We're going to number the carbons as they are numbered. So I'm going to, from my 2D, right? I'm going to number the similar carbons here on my my 3D molecular structure that I made, right? Now you can buy these from Amazon, right? You can buy your models from Amazon. The black balls are carbons. These are your bonds, and the white balls represent hydrogen, right? So let's label our carbons to match the ones in our 2D. So your carbon number 1 here is this carbon. Carbon 2, this is carbon 2, this is 3, this is 4, this is 5, and this back here is carbon number 6. So this is your your molecular structure, your ball and stick. You can ball and stick. Let's use ball and stick. Your ball and stick structure, right? And this is their 2D boat. So if you see a ball and stick, you should be able to do the correlation, right? I also wanted to show you the ball and stick because it's easier to see how close, right? The hydrogens that are on carbon number 1 and on carbon 4, you see how close they are in this eclipse position? They're right here, right? And I'm gonna look at this. They are very close and they're in an eclipse position, right? I'm gonna also bring up the shear conformation. I'm going to put 6 in the back here so you don't get confused. All right, I'm going to bring up the corresponding chair conformation for this, for our 2D, all right? And still speak to you with in terms of how close the hydrogens on carbon, the hydrogens on carbon 1 and carbon 4, how close they are. Let us bring up the chair conformation. All right, let's look at our chair conformation. All right, this is our chair conformation, right? Let's label our carbons again. So carbon 1, this is carbon 1. That, so this is carbon 1, this is carbon 1. Carbon 1 is bonded to carbon 2, this is carbon 2. That's carbon 2, this is carbon 3, carbon 4, carbon 5, carbon 6, right? Carbon, carbon 2, this is your 2, this is 3, that's 4, this is 4, 5, 5, carbon number 6, okay? Now, look at the hydrogens that are on carbon 1 and on carbon 4. Do you see how far away these two things are? This is why there is no torsional strain in your chair conformation, but you have torsional strain in your boat because these are so close. The electron clouds are repelling each other, so you're getting chaos, as I would like to say. If it's chaos, then it's confusion, it's unstable, right? So there's chaos here, so this is unstable, while this is the more stable conformation. Now, make sure you're able to explain why the chair is more stable than the boat. And also, I wanted to show you guys what the your conformation looks like if we were just looking at our 2D. So the regular 2D, your regular 2D, when you draw a regular hexagon, when you draw a regular hexagon, this is what it looks like if you do a ball and stick model. This is what the regular this is what the regular hexagon will look like if you do a ball and stick model. I think I'm going to do a video showing you how to use the ball and stick to make different molecules, etc. But these are the different conformation of our cyclohexane. Most stable, as I said, is your chair conformation and not the boat. And we literally just explained why.